Yep, galaxies can die because they're made of stars, hundreds of billions of stars. And there's also lots of hydrogen gas permeating the space between them as well that you can make more stars out of. But the thing is, stars are made out of hydrogen gas. They use that as fuel to burn. But when that runs out, a star can die. And so what happens when all your stars die off, and also you get rid of the gas between the stars that you could make more new stars out of? Well, then your galaxy would in effect die as well. Now, how long stars live depends on how massive they are. The more massive the star, the shorter its lifetime, because the more stuff you have there, then the more gravity pulls inwards. And so to counteract that stronger pull inwards, the star has to burn its fuel at a higher rate. So even though it's so much more massive than the other ones, the rate at which it burns through its fuel is so quick that it ends its life in about 100,000 years or so. These stars are the hottest as well because they're burning so much fuel at once, and so they burn blue, which might sound strange to a lot of people that hot things are blue because that's not what taps in bathrooms have been telling us for our entire lives, right? But think of like a Bunsen burner flame or a flame on a cooker on a hob, right? It's bright blue. It's much hotter than, say, a candle flame, which is more of a yellowish color, just like cooler stars that live a lot longer. So cooler stars, much smaller, things like our sun, which are, about 200 times lighter than the big blue stars. And they can burn their fuel, their hydrogen gas, at a much lazier rate. So that even though they start with a lot less hydrogen gas, like 200 times less, they can actually live for tens of billions of years. Now, the universe is only like 14 billion years or so-ish old. And so some of the smaller stars that formed at the very start of the universe are actually still kicking around today. So technically the universe hasn't been around for long enough for a galaxy to completely die and all of its stars die off. But we do see galaxies that are only made of these smaller, cooler stars because all of their bigger, hotter stars that burn very blue have all died off. They look a lot yellower, reddish in color, red being the opposite end of the spectrum to blue, but I mean, it's yellowish in color, right? And these tend to be the biggest galaxies as well. Like they've formed a load of stars over their lifetime, but now they've just been left over with all of the small stars or all those episodes of star formation. The question is though, why hasn't it made more stars? Because when a star dies, that gas gets recycled back into the galaxy again. So what's now stopping that galaxy from using that gas and making more stars out of it? If you think it through, somehow to take a galaxy from happy and lots of stars forming to nothing forming at all, you somehow have to make it an unsuitable environment for stars to form. You either have to remove the gas that you need to make more stars from that galaxy, or you need to make it so that it's not able to be used for star formation. And the way that you would do that is to actually heat that gas. Now that might sound really strange because, to form a star, it needs to be really hot and it needs to ignite. Nuclear fusion, overcome the forces repelling, pushing two hydrogen atoms together so that you can fuse them to become helium. The thing is, for it to get that hot in the first place, it has to become very dense. It has to collect under gravity to be able to do that. And the thing is, the hotter those gas molecules are, the less likely they are to collect under gravity, because the hotter they are, the faster they're moving. So they're all zipping around this galaxy at too high of a speed to be collected together. Kind of like trying to collect like overexcitable puppies together, right? If they're super tired, it's dead easy to collect them in one space, but if they've got 2 tons of energy and you're trying to like collect them all together into one place, you're gonna struggle. I don't know, the analogy worked in my head a minute ago, I'm sticking with it. So we call any process that can cause this shutdown of star formation, either through removing the gas or heating the gas, a quenching process. The star formation has literally been quenched. And figuring out the processes that can cause quenching was basically what my entire PhD thesis was on, which one day I will make a video on what I found. But I think today I just want to talk through some of those processes, kind of like a quenching 101. So first up, we can split quenching processes into two categories, right? The things that happen internal to a galaxy and the things that happen externally to a galaxy. You can think of it as like nature versus nurture, you know, that they talk about in biology all the time, like how someone is raised. Is it their nature that makes them that way, or is it the way that they have been nurtured by family and friends around them? So for a galaxy, external things that happen from the outside, so something to do with its environment, and internally, something about the galaxy itself that can prevent it from making more stars. Of course, just like politics, it's never a 1D spectrum, is it? It's always 2D. And so for our Quenching 101 in 2 dimensions, actually we also can split things in terms of how fast they act as well. So are they very rapid processes that cause like an immediate shutdown of star formation? Or are they a much slower process that sort of slowly lowers the rate at which a galaxy forms new stars over time until after, say, billions of years, it's managed to stop it forming them fully? And so us astrophysicists like to classify quenching processes on this diagram in terms of whether they're fast, slow, external, or internal. They lie scattered across this entire diagram. So I figured let's go through them one by one of what processes can cause this. So let's start in the rapid external part of the diagram with a process that I think a lot of people generally have heard of, and that is the idea of a galaxy merger. So a collision of two galaxies so that they become one galaxy. And that's due to happen to our own Milky Way galaxy. It's going to merge with the Andromeda galaxy in a couple of billion years' time. It's ages away. You don't need galactic collision insurance, I promise you. And this is all because the two galaxies are coming together under the force of gravity between them, which is strong enough to overcome dark energy, which is causing the expansion of the universe on those small scales if they're close together. And no two stars will collide in that merger of two galaxies either, because the space between stars is just so big. What does happen though is that the hydrogen gas that fills the space between all of the stars in a galaxy does collide, and where that collides you get shock fronts. It's incredibly dense and it triggers a lot of star formation, so much so that you get these huge star bursts in galaxies that are merging, like way in excess of any normal star formation rate that we see in other galaxies. You know, usually we see like 1 to 2 solar masses, so the mass of the sun, per year forming in galaxies, but in star bursts you can be forming like 100 to 200 times the mass of the sun per year in stars in a starburst. Which you might be thinking, well, that's the opposite of quenching, Becky. But if you think about it, if you use all your gas up very quickly in this one go big or go home bender event that the galaxy has, then you're not going to have much gas left over for your next generation of stars. And so you very effectively cut off the star formation rate very quickly by using it up too quickly. The thing is, obviously, when those stars die, they're going to recycle that gas back into the galaxy. And you think, well, then it'll be back again after another 100,000 years or so for it to use it to make more stars again. The problem is, in a galaxy merger, the gravitational forces between these two galaxies means that everything sloshes around for a good billion years before the galaxy settles back down. But when that happens, you inject so much more energy into that gas and you slosh it around so much that you give those gas particles more energy again. And so they heat up, and essentially you heat all the gas in the entire galaxy, so much so that none of it is then useful for star formation. So yes, you cause these big starbursts, locking away a load of the gas that you would use at later times, and then you heat, sort of stirring the pot, all the rest of the gas that you could have used that was left over, so that it can never be used again, and you end up with the remnant of the galaxy merger just being this big blob of a red and dead galaxy that has no stars forming in it anymore. And this explains why the majority of the dead galaxies we see are the most massive, because they've got that way by merging together. Now, you're going to get a lot of galaxy mergers when you have galaxies really close together in a very dense environment. And that all depends like sort of where in the universe this galaxy actually is. Because if we could sort of zoom out on the entire sort of structure of the universe, when we simulate what happens if you start off with just a big soup of hydrogen in the early universe and sort of run the simulation through of how gravity affects that, you end up forming this really cool web of like filaments that intersect. And along that web is where you get all the galaxies forming, because well, that's where the most stuff is for them to form from. And when the filaments intersect is where you have a node and you get a big group or cluster of galaxies grouped together. You then have voids all between it as well. And we think the Milky Way and Andromeda are actually in quite a big void in our universe. But actually, by having galaxies close together, even if they don't merge, you can quench the galaxy's star formation rate, albeit at a much slower rate than the sort of instantaneous way that mergers do it. So we've hopped over to a sort of external slow side of our diagram now with things that we call environmental quenching. Basically, whether the galaxy is alone or not, we call a galaxy's environment. Because the thing is, when you get galaxies in these big groups, you have a lot of gas in that node where all those filaments intersect as well. And because all of these galaxies are very energetic and sort of moving around this big group and clump of galaxies, you heat that gas again, so much so that it actually glows in X-rays, and we can actually detect that and see that it is incredibly, incredibly hot. Now you can imagine a galaxy that's been relatively left alone all its life gets captured by the gravity of one of these big groups or clusters of galaxies, and it starts to infall onto this group and this very hot gas that's glowing in X-rays. And you can imagine the effect that that has on the nice, pristine, cold hydrogen gas that this galaxy has to form new stars with. So there's a couple of different processes we think happen. First one's called ram pressure stripping. That literally means that like the galaxy feels a wind as it infalls on that group because of this hot gas. I had this explained to me when I was a grad student as like riding a bike so fast that all of your hair falls out. And it's safe to say that I have been terrified of riding bikes ever since, because not my hair, anything but the hair. Another process you could have is thermal evaporation, which essentially means as the cold gas hits the hot gas, the cold gas heats up, and then you can no longer use it for star formation. My favorite is viscous stripping, which is such a fun phrase to say, but it's all to do with the fact that the cold gas is actually really slow moving, whereas the hot gas of the group and cluster is moving very, very fast. And so you set up these outflows out of the galaxy because of the interaction of the two. Then you've got something called harassment, which can happen to any galaxy in the group, whether it's infalling or not. You can imagine them sort of like whizzing around on orbits and having very fast flybys with other galaxies in the group. Not merging because they're moving so fast, but lots and lots of repeat interactions where the gravity just sort of pulls on it a little bit as it goes, and again heats up all that gas inside the galaxy that it could use to make more stars. I clearly like to represent all of those processes with emojis because if you look at them, they read like a Quentin Tarantino movie script. And sometimes you just need a little bit of joy injecting back in to these horrific sounding processes. On the opposite side of the spectrum though now, galaxies left alone in voids all their lives, you know, just to their own devices, you would think would be completely fine. They'd be safe from all this viscous stripping and collisions and mergers and everything. But actually that's not the case. The galaxy's nature can actually cause it to stop forming stars. So first of all, something we call morphological quenching. So morphology essentially is the shape of a galaxy. What shape is it? And this is essentially saying the shape of the galaxy can affect how many stars it could be forming. So people think about what galaxies look like. You always picture the big, grand, beautiful spiral arms like we think our Milky Way has. But the thing is, those beautiful spiral arms can actually funnel gas from the outskirts of the galaxy and dump it into the very center of the galaxy, where it's incredibly dense, you've got a lot going on, it's very energetic. Stars, instead of being on nice, ordered, sort of flat, nice disk rotation, can be on orbits a little bit more like a beehive. Like they're all still orbiting, but it's very chaotic. So it's very energetic there. So by taking that gas from the outskirts and funneling it into the middle, you're going to heat that gas a lot. And again, hot gas is useless to a galaxy. It can't use it for star formation. So the majority of spirals we see are very blue, beautiful, picturesque galaxies. But then actually about 30% of them are these red and dead galaxies. And they've gotten that way because they've essentially funneled their gas away from where it's needed and dumped it in the middle where it can't be used. It's especially apparent when you have a spiral galaxy with this bar structure in the middle as well, this like long, thin structure where the spiral arms come out the outside. We think, it's not confirmed yet, people are really trying to prove that this is happening, but we think that that process is much stronger when you have a bar. There's also something called mass quenching as well, which is where the most massive galaxies are more likely to be quenched as well. And people think that's all to do with the supernova, essentially. Yes, okay, supernova do recycle the gas back into the galaxy, but if you form lots and lots of stars to get that massive, then you're going to have a lot of supernova. A lot of supernova injects energy back into the galaxy and could also even expel the gas if they're particularly energetic. So a lot of supernova means you heat your gas, and again, you can't use it for star formation. So galaxy gets a bit greedy and it can end up shooting itself in the foot. So these processes which can funnel gas to the center, not just the morphological quenching, but mergers do that too, as sort of stuff sloshes to the middle, can actually trigger another process that acts internally to the galaxy, but very rapidly. Hopping over now to our last quadrant in our diagram. Something that can act from the inside and cut something off that rapidly needs to be very energetic. So what's at the center of every galaxy? A supermassive black hole. And if you feed gas to that supermassive black hole, it is going to start eating it, a process that we really call accretion. Accretion just means collecting stuff under gravity. And the way black holes do that is that material comes in, it starts to spin around the black hole, and you'll know if you take a ball of pizza dough and you set it spinning, it ends up coming out into a flat disk. So you get these really cool disks of very, very hot, very fast-moving, spiraling material around these supermassive black holes if you feed them with lots of material in the first place. But the thing is, the black hole isn't just this endless hoover. It can't just eat as much material as it wants to. It is limited by the fact that there is a pressure with how much stuff you can get into that disk at once. And sometimes if you overload it, then what happens is you get an outflow from that disk, not from the black hole, because, when stuff's crossed the event horizon, nothing can escape because it can't travel faster than the speed of light. But you can get an outflow of material from the accretion disk. And sometimes, if there's big magnetic fields as well, that can all get funneled into these huge jets that are light years long, bigger than the galaxies themselves. And you can imagine that much energy being pushed out back into the galaxy from these outflows that are, again, close to the speed of light. They're so energetic and so hot. Of course, that's going to either heat the gas or it's going to expel the gas that you're going to need for more star formation. Now, this is a process we call AGN feedback. AGN, active galactic nuclei. So the black hole in the center is active. And feedback because, well, by feeding the black hole, you've ended up with this feedback loop of stopping the galaxy from forming more stars. Now, some of you will have noticed that on that plot, AGN feedback has a big question mark after it. And essentially, that's my job at the minute, is to try and get rid of that question mark. It's what I spend my research time doing. Because the thing is, theorists are convinced we need AGN feedback in simulations to make them match observations that we make of the universe with telescopes. The thing is, we haven't really found any direct evidence for it happening in observations. We have indirect evidence, so we find the most AGN between the very blue galaxies and the very red galaxies, sort of in the green colours. We call it green, it's obviously not actually green. We find them there, which suggests that they could be causing this process. But we've never found any statistically significant fall across the entire population of, say, 1 million galaxies of this actually happening. We haven't found the smoking gun. And it's that smoking gun that I'll be looking for when I get back to looking at my data at my desk tomorrow. I was just thinking, the last time I wore this outfit to film, everyone in the comments dubbed it my Harrison Ford outfit because of this little waistcoat thing, which, you know what, I'm just gonna own it. I love this Harrison Ford outfit. And they can burn their fuel at a lot of, and they can burn their hydrogen gas, their fuel, at a lot of a lazier rate. And they can burn their hydrogen gas, their fuel, at a much lazier rate. And they can burn their fuel, their hydrogen gas, at a lot of a lazier rate. And a much lazier. He's still kicking around today. Dribbly nose, that's not cool, I got a dribbly nose. Quench, quench, baby. Quench, quench, baby. Doo-doo-doo-doo. So by the time this video comes out, I'm not going to be at home. I'm going to be visiting somewhere, filming some videos. And I am so excited. It's a place I've never been before. They've invited me to come and film. And I am like, kid on Christmas. So, I mean, I'm probably going to have blabbed on Instagram or something about where I'm going before now. But, you know, leave your guesses in the comments and we'll see if you're right in a couple of weeks.